Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a very nice equation with complex numbers. We have 1 plus I to the power n equals n squared. In this case, n is an integer. Now where does this problem come from? Well, problems come from different resources or sources. Sometimes I come up with the problem, which I usually call homemade. Sometimes I take them from books, websites, so on and so forth. Sometimes friends give me some ideas. And this problem was suggested by Pepe Briguglio. Thank you for the idea. Let's go ahead and take a look at this problem. So now, n is a positive integer, first of all. Or we can call that a real number, I guess, right? Not necessarily an integer. Let's just call that a real number. So we have 1 plus I to the power n equals n squared. Now, we know that n squared is a positive real number, so the left-hand side must also be a positive real number. I guess in this case, doesn't really need to be specified that it's an integer, because what we care about is we have a non-real complex base, which is 1 plus I, right? But as a result, we want to get a real answer. Okay, so let's go ahead and start by turning 1 plus I to the polar form. Thanks to Euler, we can write any complex number using an exponential, which is actually huge, because from there we get a lot of good identities as well as the most beautiful equation. So here's how it works. In the coordinate plane, which we also call argand plane, we have a point or vector, which we designated as z equals a plus bi, a being the real part, and b being the imaginary part of our number. So we can basically plot a complex number as a point, and then of course we can talk about the angle it makes, the positive angle it makes with the real axis, and then so on and so forth. And distance from 0, of course, that'll be the absolute value. By using those two values, and absolute value is also called r, which is the modulus, you can write z as r times e to the power I theta, which is a very, very compact form. And the best part about it is you can take two complex numbers and just multiply very easily, because all you have to do is multiply the moduli and then add the arguments. Argument is the angle, by the way. So in that sense, 1 plus I can be written as square root of 2 multiplied by e to the power I times pi over 4. The reason being square root of 2 from the Pythagorean theorem is the distance from 0. If you draw a right triangle, you're going to see what I'm talking about. So now let's go ahead and raise this to the power n, right? And what is that going to turn into? First of all, square root of 2 can be written as 2 to the power 1/2, right? And then you're going to raise it to the power n. So the powers will be multiplied. So that gives us 2 to the power n over 2. And then what's going to happen to the argument, or the exponent in this case? You're going to get e to the power I pi over 4 times n, which is e to the power I n pi over 4. Okay? So far, so good? All right. Now, this is what we have. And then, of course, this needs to equal what? N squared, right? Great. Now, in this case, if n is an integer, solution should be fairly easy, don't you think? But here's what we need to do. How do you compare a real number with a complex number, right? First of all, the right-hand side is a positive real number, so the left-hand side also needs to be a positive real number. Okay, so obviously the n squared is the modulus of n squared. So the moduli need to be equal to each other, right? In order for two complex numbers to be equal. So in this case, we have that 2 to the power n over 2 equals n squared. Okay, we'll get to that equation in a little bit, but let's go ahead and take a look at the second piece. There is nothing here, but we can definitely write this as e to the power 2 pi ki as a multiple of 2 pi, right? K is an integer in this case. So how do we set these two things equal to each other, right? So in order for this to work, we basically need that n pi over 4 needs to be a multiple of 2 pi, like this, right? 2 pi k. So how is that possible? N pi over 4 is equal to 2 pi k. You can also write this as a mod or modular arithmetic identity or equation. You can say n pi over 4 needs to be congruent to 0 mod 2 pi, which means it needs to be a multiple of 2 pi. Same idea, just written differently. Okay? So this is what we have so far. So where do we go from here? Let's go ahead and take a look. Well, first of all, if you kind of look at this equation, cancel out the pi, you're going to end up with something like n equals 8k. All right? So that means n needs to be a multiple of 8. What about the right-hand side? Same idea. If you multiply by 4, you're going to realize that n needs to be a multiple of 8k. Why? Because what is congruent to 0 mod 2 pi? Multiples of 2 pi, right? So this needs to be congruent to 2 pi k, and it's going to be the same idea. All right. Now, so far we got n equals 8k, and 2 to the power n divided by 2 equals n squared. So can we kind of solve this as a system? Maybe, right? Since n is a multiple of 8, we can replace this with 8. So this is going to look like 2 to the power 8k divided by 2, which is 4k. And on the right-hand side, you're going to get 8k quantity squared. From here, we're going to get 2 to the power 4k equals 64k squared. And then 64 can be written as 2 to the power 6. If you divide both sides and subtract the exponents, you get something like this. And at this point, it's kind of like guesswork, don't you think? You're basically going to be looking for some number that will give you a perfect square when you raise 2 to the power 4k minus 6. So that's one way to approach it. Another way to approach it is basically going with this directly and using logarithms. Let's go ahead and take a look at that. Log both sides base 2, okay? And that's going to give you an identity because log is 1 to 1. And then from here, you can basically move this to the front. That gives you n over 2 is 2 times log n with base 2. Awesome. You can multiply both sides by 2. N equals 4 times log of n base 2. And then this is what we end up with. Now, it's actually kind of easy to check for small values of n. Obviously, n needs to be a power of 2 in this case. So let's go ahead and check for n equals 2. If n is equal to 2, we get n equals 4 times 1, which is 4. Uh-oh, that doesn't work. If n is equal to 4, then you're going to get log 4 with base 2, which is 2, because 4 is 2 squared. And then 2 times 4 is equal to 8. If n is equal to 4, then n equals 8. Again, that doesn't work, so x. And then now we're going to check n equals 8 next. And that's going to give us, if n is equal to 8, n equals 4 times log 8 with base 2, which is a 3. That is going to be a 12. Again, that's an x. And if you try 16, which is the next power, you're going to get n equals 4 times log of 16 base 2. This is 4, remember. 16 is 2 to the 4th power. 4 times 4 is equal to 16. So yay, we have success, which means n equals 16 works. Awesome. Now, what happens if n is greater than 16, right? Obviously, and I hope you can see this too. If n is greater than 16, the exponential 2 to the power n over 2 is definitely going to go much, much faster than n squared. So you got the equality. That'll never happen again. So, and of course, n equals 16. 16 is divisible by 8. By the way, we knew that n is a multiple of 8, so we didn't even have to test 2 and 4. But anyways, we just did. No big deal. N equals 16 happens to be the only solution to this equation. Now, let's go ahead and check it out. If you plug it in, 1 plus I to the power 16. One thing to keep in mind, squaring 1 plus I is actually fairly easy because it'll give you 2i, and then from there you can proceed. So let's go ahead and break it down like this. This will be 2i to the 8th power, and that'll be 2 to the 8th power times I to the 8th. As you know, 8 is a multiple of 4, so this is going to be 1, and this is going to be 256, which happens to be 16 squared. So as you can see here, n equals 16 actually satisfies this equation. Let me write it this way so you can clearly see that 16 indeed is a solution. And let's kind of color code it a little bit, okay? So I'm going to go ahead and use a different color here. And as you can see, 16 is indeed a solution. And that's the unique positive integer solution. And This brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. Until next time with another video. Until then, be safe. Take care. I just want to raise a question real quick here. Do you think there are non-integer solutions to this equation? And if so, how can we find them? Until next time, bye-bye.